everyone, I am Avleen Malhi from Aalto University presenting OMI ODF open standards which are a core component of bIoTope project. With advancement of ICT and sensor technology, Internet of Things is expanding. With expansion of IoT, many companies are moving to data-driven business model by creating different services to their customers. Hence, data became their main asset. These companies are creating their own IoT architecture for data collection, resulting in vertical silos. In large-scale environments such as smart city with several domains such as water management, healthcare, smart home, transport systems, which coexist in parallel. The existing model of creating one system and one company create vertical silos resulting in effective use of available data assets and limited service. Think about an advanced journey planner where citizens could avoid pollution. You would need to integrate air quality data with public transport. In large-scale systems like smart cities, multiple domains will coexist and need to interoperate to create advanced services. When an IoT solution has been created to cater only one domain or use case, it won't automatically communicate with another systems. The lack of coherent interfaces has become one of the critical bottlenecks for developing system of systems. Existing standards are domain or lifecycle specific. In essence, we have only intranet of things. Vertical silos prevent the creation of cross-industry, cross-platform, cross-organizational services due to their lack of interoperability and openness. What is interoperability? The ability of two or more systems or components to exchange information and to use information that has been exchanged. It means interoperability can be broken down into two keywords, exchange and use. Hence, we define interoperability as two-level challenge, communication level and data level. The communication interoperability provides path, infrastructures, and mechanisms for data exchange between two or more distinct organizations, networks, applications, and IT solutions. Communication level interoperability is also divided into two levels, technology and interface level. The technology level interoperability can be achieved by a common agreement of the data transmission medium, low-level data encoding, and rules of accessing the medium, for example, TCP. The interface level interoperability should provide the necessary communication interface which allows systems to communicate with each other for exchange of data or information whenever needed, whoever needed, and whatever needed. Data level interoperability should deal with the structure and semantics of data to make systems interoperable. It can be broken down into syntactic and semantic interoperability. The syntactic interoperability refers to the shared format and structure of data that has been exchanged, whereas semantic interoperability deals with the shared meaning of it between the heterogeneous systems that are designed for different purposes. To enable openness and interoperability, we propose Open Messaging Standard as a possible solution. Open Messaging Standard is an application-level protocol which enables peer-to-peer near real-time communication between devices or systems. This standard enables four types of interfaces to access data, which are create, read, update, and delete. It consists of two standards, ODF and OMI. Open Data Format (ODF) is data payload for IoT applications. Open Messaging Interface publishes and consumes real-time information between systems or devices through its interfaces. Open Data Format is the open group standard for data format. It is defined as a simple ontology and specified using XML schema. It provides structure and mechanism to annotate data for information exchange. It enables requesting and sending published data between systems and is generic enough for representing any object and information. As the figure depicts, it allows hierarchical structure for objects and allows RESTful queries. Open Message Interface (OMI) enables communication between heterogeneous devices and information systems. OMI properties include self-contained messages, protocol-agnostic messages, different payload formats, specifying time to live, publication and discovery of new services and metadata, and subscription of data or services. The various OMI operations include write, read, and cancel. The write operation allows to write information such as sensor values, set points, alerts, etc. Read operation allows to get current and historical information, alerts, and other events. It also allows to subscribe information with or without callback. Cancel operation allows to cancel subscriptions before TTL expiration. In the given figure, the upper rectangle represents OMI write interface and lower rectangle represents ODF message. Finally, the takeaway of this presentation is Open Messaging Standard, which enables openness and interoperability for data exchange between two or more heterogeneous systems. OMI provides interface-level interoperability, whereas ODF provides syntactic-level interoperability through its structure and also provides mechanism to annotate data for semantic interoperability. The OMI messaging standard has been implemented in messaging middleware called OMI reference implementation. OMI ODF is an open source implementation developed at Aalto University and can be downloaded from the provided GitHub link. This reference implementation enables quick deployment of IoT node for peer-to-peer communication. The reference implementation has two components, namely OMI node server and web client as shown in the figure. OMI node server is the main component of this reference implementation and it supports all OMI operations. The major task of node server is to handle incoming requests and to manage database. It also has agent management system which interacts with core OMI node to push and pull sensor data from database and request. It has two types of agents, external and internal. External agents are designed in a way that they can communicate with plain TCP socket. It works by creating ODF formatted XML data gathered from sensors and sending it to the configured port via Keep Alive TCP connection. Internal agents are extended threads that perform internal functions. These agents are listed in configuration file. Graphical user interface is for end users and for developers to create and test OMI messages in deployed OMI node server. It allows automatic creation of OMI ODF messages. It is actually a sandbox for testing OMI operations or features. Now we provide guide for deploying OMI reference implementation. The details of the deployment guide are shown in the current slide. OMI reference implementation is Java 1.8 dependent. Any developer or user who want to deploy should follow the 5 steps provided as listed. For further information, please check the provider links.